Swayam Prabha. Digital India. Educated India.
Hello, so welcome to Astrochemistry. This is lecture 23, and today we're also going to be conducting this session as a tutorial. This is the 5th tutorial. Recall that we've already had 4 tutorials in the past. Now we're having this tutorial because we've introduced enough concepts so that before proceeding to the next idea, we should actually be looking into some problems and solve them based on the concepts we looked into in the past few lectures, which is based on the properties of molecules found in space, and also concerned with an introduction to the different types of motions of molecules, etc., etc. Okay, so on that note, we shall begin into this. We shall get into this tutorial session right away. Okay, so as always, the questions will be written on the board and the answers will be discussed. Okay, yeah. So the first question is going to be that in the last lecture we looked at molecular rotations in lectures 22 and 21. Okay, right? In lectures 22 and 21, we looked at the rotation of molecules, the translation of molecules, the rotation of molecules, the vibration of molecules, and I gave a very brief introduction to change in electronic states. Okay, now the energy is required. Okay, right? In general, okay, the energy is required for each of these transitions fall in a particular range in the electromagnetic spectrum. Okay, the energy is required for these transitions, the energy is required for these transitions in molecules correspond to various regions in the electromagnetic spectrum. The question, so this is the statement. Okay, we looked into this, and I'm telling you that the energy required for molecular translation, rotation, vibration, etc., etc., right, they fall into some region of the electromagnetic spectrum. Okay, now what are the question is, what are the prominent regions? In short, okay, right? Of course, for each individual molecule, the exact region is going to be different, but we can still get a range. We can map a range associated with each type of motion. All right. So the answer is that the rotational motion, okay, of when I say rotational motion, I'm talking about the pure rotational motion. Okay, the rotational motion of molecules, especially of interest in astrochemistry, okay, of interest in astrochemistry, right? The energy for this molecular rotation, it happens to be coincidental with the energy range of the microwave region. Please note this. So what is the wavelength range for the microwave region? It is going to be 10 to the power minus 3 to 10 to the power 1 meters, right? And this is the wavelength. What is the corresponding frequency? it is going to be approximately 3 into 10 to the power 9 to 3 into 10 to the power 11 hertz. This is the frequency. All right. You can also, use the E equals hc over lambda to find the energy region, the energy range. Okay, right? And we're talking about, molecules, corresponding to, let's say they have a total of 10 atoms or max, or max up to 20-ish atoms. Okay, so for these atoms, the rotational motion happens in the microwave region. Okay, similarly, okay, right? Similarly, the vibrational motion of molecules, the same, of same relevance in astrochem. Okay, molecules of same relevance in astrochem. That happens to fall in the infrared region. Infrared region plus microwave region also. And notice that occasionally note the vibrational, the vibrational motion of molecules is typically coupled with rotational motion also. Are we clear? See, because vibration involves rotation. Vibration is of higher energy than rotation, but not by so much. Okay, right? So in many cases, the vibrational motion of molecules is actually coupled with the rotational motion also. Please note this point. Okay, right? So the vibrational motion corresponds to the IR region and microwave region. And of course, the IR region is vast. Okay, if you recall, there are different regions of the IR. It ranges from approximately 10 to the power minus 7 meters to 10 to the power minus 3 meters. Okay, the region closest to microwave radiation, okay, the microwave region, the IR region, which is closest to the microwave region, that is where the molecular vibrations of molecules of interest in astrochemistry. Okay, we're talking about the same number of atoms. For these type of atoms, the molecular vibration happens here. All right. Now, in general, the molecular vibrations happen in the IR region, and not just the region closest to the microwave region, but throughout the IR region. Are we good? So vibrational spectroscopy, and that is why while we understand rotational motion, we typically resort to what is called as microwave spectroscopy. Similarly, when we want to understand the vibrational motion of molecules, we resort to what is called as infrared spectroscopy. Are we good, right? And please note a point. Just the fact, okay, the fact that this happens to be coincidental with the microwave region, that is the rotation, and the vibration happens to be coincidental with the infrared region, that itself tells you that rotation is a lesser energy process than vibration, because the IR region, right? The IR region is actually a higher energy region than the microwave region, because again recall, E is hc over lambda, right? E is hc over lambda, so this is less than 10 to the power minus 3 meters approximately. Okay, right? So E is hc over lambda, and as the lambda decreases, therefore, right, as the lambda decreases, the energy of the electromagnetic radiation increases. All right. Now, the next thing we are going to see is, I will now delete the question itself, okay, because you've had it for enough time. The next region we are going to look into is change in electronic state. Okay. And that typically coincides with what is called as the UV region, the ultraviolet region, plus some part, okay, very little part of the visible region. All right. So the change in electronic state corresponds to this region. We're not even going to be concerned with translational motion because the energies required are so small, okay, are so small that they perhaps don't even fall in the radio wave region. Are we clear? Okay. So therefore, the key thing to understand is that the electronic state, okay, the change in electronic state typically happens in the UV region and some little part of the visible region also, especially for molecules of interest in astrochemistry, all right? Whereas the rotational motion happens in the microwave region and the vibrational motion happens in the infrared region. And so you kind of get an inkling about the relative magnitude of energies involved, and also the various frequencies, right? And the wavelengths wherein you can expect the signals, the spectral signals to actually show up. Are we clear? Okay. So that is the relevance of this question, to give you an indication of the magnitude of energies involved and exactly in which region what transition can be expected. All right. So on that note, I'll go on to the next question. This is going to be page 5, and the next question 2 is true or false. Typically, changes in electronic state, right, of any molecule are accompanied with changes in the rotational and vibrational states of the same molecule. What do you think is the answer? What I'm saying is that, typically when the electronic state of any system changes, recall in the last lecture I gave you an example of how in an H2 molecule, the transition, the electronic state can be the promotion of an electron to a higher energy anti-bonding orbital, the sigma to sigma star orbital, right? I gave that brief example. So while the electronic state changes, the rotational and vibrational state also typically change. Is it true or false? As an expectation, can I expect fairly that along with electronic state change, the rotational and vibrational change will also change? What do you think is the answer? Well, the answer is logically true. Because, why is that? Because as the energy required for electronic transitions, recall that happens in the UV region, right? Whereas these happen only in the IR and the microwave region, respectively, right? Yeah. So therefore, the energy required for electronic change is really high, okay? Because your E electronic transition, I'm going to call this as E electronic, right, is very much greater than E vibration, which is greater than E rotation. Whenever this transition happens, right, it's always accompanied by these two also. So please note this point, okay? I mean, this point will be of relevance when we actually look into examples of how molecules are detected in space and we look into their individual spectra themselves, okay? So please note for now that whenever electronic motion happens, along with that, vibrational and rotational motion also happens, all right? That's the significance of this question. We'll now move on to the next question, which is 3. What is a polar molecule and what is the significance of the idea of polarity, right, in getting spectral signals? So this is a new concept, right? Although any chemistry major and a physics major also. If you have taken up chemistry or physics in your 11th and 12th, you may have some idea about the idea of a polar molecule, right? And it turns out that this concept of polarity is exceptionally important in astrochemistry, right? Because the concept of polarity is what is going to tell you whether or not it's going to be easy to get a spectral signal. Okay, so because polarity is connected with spectral signals, right, and because it is two spectral signals that you detect molecules in outer space, overall the concept of polarity becomes very important in astrochemistry itself. That is the significance of this question. What is the answer? The answer is going to be that, okay, right? So by a polar molecule, I mean a molecule whose net dipole moment is non-zero. All right. So of course, some molecules are much more polar and some are much less polar. But as long as any molecule whose net dipole moment is non-zero, I'm going to call it polar. Right. Now, as part of answering this question, right, I have introduced one more term, one more jargon called as dipole moment. What is dipole moment? It's very simple, right? Whenever you have, like any 2 point charges separated, right, or any charge distribution separated, right, which we assume to be some sort of a point charge, right, separated by some distance, a dipole moment, okay, right, a dipole moment which is given the formula, mu, okay, right, dipole moment is given the formula mu. I'm going to call this the magnitude of the dipole moment. It's a vectorial quantity, okay. The magnitude of this is going to be nothing but the charge, okay, on the charges, okay, right, the charge on the different charges, right, times the distance between them, the magnitude of the distance. So this is going to be called as a dipole moment. All right. For example, you consider a molecule such as carbon monoxide. From CO plus minus. If you consider, like this resonance structure of carbon monoxide, you understand that, there is a net delta plus charge here and a negative charge here, right? So this system will possess a net dipole moment. So therefore, this is an example of a polar molecule. All right, this is an example of a polar molecule. And the dipole moment, right, as the charge times, we can call it QR or something, QR. And the SI unit is going to be coulomb meters, right? Distance in meters and charge in coulombs, right? Yeah. Whereas more conventionally, the units are measured in something called as a dBi, okay? And 1 dBi, is a very small amount of coulomb meters. The exact magnitude I forgot. I will come back to it and tell you in the next tutorial, okay? There's some very small, small. We're talking about something like 10 to the power minus 30 odd, okay? So if I recall correct, it's 3.3 into 10 to the power minus 30, but I will confirm in the next class, okay? Some small amount, roughly, 10 to the power minus 30 coulomb meters, I think. All right. So this is the magnitude of a dBi. So CO is an example of a polar molecule wherein overall there is a net dipole moment. All right. Let's look at a few more examples of molecules which have dipole moment and which do not have dipole moment, and then I'll address their importance in the context of getting spectral signals. Okay. Now consider, another example now of the molecule of N2. Right? You take the example of a molecule like N2. Now, the two N nuclei are represented by the N symbols here, and in between them is the electron cloud, which is what we overall call as a triple bond. Okay, right? Now, is there any net charge separation here? Because eventually, like it's a homonuclear diatomic. That is, both the nuclei are the same. Unlike carbon monoxide, where the two nuclei were different. Okay, so here you see that there is no net dipole. In other words, any temporal excess charge built up here, right, is going back to the same molecule here, is going back to the same atom here, will be exactly cancelled by the opposite amount there. Okay, right? So there is no net buildup of partial charges anywhere. All right. So in all of these homonuclear diatomic molecules, for example, H2, and then you can think of O double bond O, etc., etc., right? And all these homonuclear diatomics, okay, they are all non-polar, and the net dipole moment is 0. All right. So these are examples of non-polar molecules because the net dipole moment is 0. Now see, there can be some more molecules, right, wherein each of the individual bonds may possess a dipole moment, but the molecule will overall be non-polar. What's a simple example? Take the example of, for example, carbon dioxide. And no load pairs on carbon. So if you notice this, with respect to this particular C double bond O bond, okay, this is going to be getting a delta minus overall, right? And this is going to be, let me call this like delta 2 minus, the partial charges due to the difference in electronegativity between this carbon and oxygen. And as a result, there is going to be delta 1, I'm sorry, this is going to be like delta 2 plus here, right? Similarly, due to this oxygen, right, there is going to be, once again, there is going to be some dipole moment in this direction. Okay, right? I mean, it's typically represented like this. Sorry for the bad depiction, something like this. Okay, now for this bond, okay, because again the same oxygen, right? It's again the same oxygen. Again, it's also going to be delta 2 minus and delta 1 plus here. Okay, right? So therefore, because the magnitude of this delta, if this is delta 2 minus, this is also going to be delta 2 minus. All right. So because both of this is the oxygen, right? There is no 2-1 business at all. I thought of initially, using different indices to indicate what will happen. But because this oxygen and this oxygen are both the same, the amount of accumulation, okay, the net amount of accumulation, right, is of charge is going to be overall 0. So overall, net dipole moment is 0, right? And it's a non-polar molecule. Okay, so please understand that. In a molecule such as carbon dioxide, despite the individual bond possessing a dipole, the net dipole cancels out, because whatever dipole is created due to this moiety is exactly cancelled out by this moiety, because dipole is a vector, right? So if it's of the same magnitude and then they operate in different directions, the net dipole moment cancels out. So this is also another non-polar molecule. Say for example, I'll give you just 2 or 3 more examples to illustrate different chemical principles and their relevance in astrochemistry. So consider, for example, SO2. Now SO2 is bent, and not because of the excess. Wait, how many electrons does it have? If you consider valence electrons, it's going to be 18, right? So 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16, 17, 18. Yeah. So there is one lone pair of electrons on sulfur. That is what makes it bent and not linear, right? Now, because of this bent structure, right? Let's say, O is more electronegative than sulfur, right? So there is going to be a dipole, which is typically indicated as going from the positive side to the negative side, right? And this is going to be here, right? So there is no cancellation. You get my point, right? Here, because it's linear, there was exact cancellation. Here, there is no net cancellation. Therefore, there is a net dipole moment, and the molecule is going to be polar. Okay. So as far as heteronuclear polyatomic molecules are concerned, sometimes the symmetry in the molecule could cancel out the net dipole moment. Yet another case where the net dipole moment cancels despite the molecule having a 3-dimensional structure would be something like this, CCl4 or like CH4. What's the shape of CH4? It's going to be tetrahedral, right? If you consider carbon to be, in the middle of a tetrahedron, and that this CH2 to be in one plane, right? Let's say it's coming in the plane of the board, and this hydrogen to be coming towards us, and the other hydrogen to be going away from us. The hydrogen coming towards us denoted by the solid line, and then the hydrogen going away from us denoted by the dashed lines. Okay. In this case, right, the net dipole moment again cancels out. Why is it? How does it cancel out? Because whatever is the electronegativity difference between the individual CH bonds, right? So let's say, between carbon and hydrogen, carbon is slightly more electronegative, okay, right? So this is going to be delta plus, and this is going to be delta minus, slightly, okay, right? So because carbon is slightly more electronegative, the dipole moment is going to be from here to here, okay? Now, similarly, so this and this will cancel out, and this and this will cancel out, okay, right? So overall, the net vector sum of the dipole moment is 0. So the point is no net dipole moment, and this is therefore non-polar. All right. So I just was giving you, a few examples of molecules which can be polar and non-polar due to different reasons. The overall point being that even though individual bonds in the molecule can possess a dipole moment, the molecule itself can overall be non-polar. All right. And one has to basically look into the symmetry of the molecule, right? Its molecular formula and the symmetry. And based on that, we can decide whether a molecule is polar or not. Now we come to the next part of the question. The next part of the question is, what is the significance of the idea of polarity in getting spectral signals? Let's discuss this step by step. Let's start off with rotational spectrum. All right. So polarity and spectra. Now please note that, okay, for any molecule, right, if you want to get its purely rotational spectrum, right, the molecule should be overall polar. Should be polar. Now, I haven't explained the reason to you why, okay, right? The reason actually follows the laws of quantum mechanics. One can actually derive it, okay? But in this class, we won't be looking into it, okay? But please note that for a molecule to actually first to be getting the rotational spectrum of the molecule, it should be polar. For example, H2, we cannot obtain the purely rotational spectrum. I mean, I'm talking about, the symmetric H2 where both the isotopes are the same. All right. So please note that I haven't told you the reason for why, the molecule should be polar for it to be obtaining, for us to be obtaining its purely rotational spectrum. This is a consequence of results of quantum mechanics, which we shall touch upon very briefly in a subsequent lecture. But for now, please note through this tutorial question that if you want to record a spectral signal, a rotational spectral signal, a purely rotational spectral signal of a molecule, the molecule should be polar. And so for hydrogen, you cannot obtain. Similarly, for methane, also, this is true. All right. So on that note, I end this tutorial. And in the next tutorial, we shall be continuing with the same question. And I will be addressing some more points also. Thank you so much.